Welcome to the solution video for the Discrete Math 1 Midterm 2 that I wrote at trevtutor.com. You can check it out there in the Discrete Math 1 section. So if you want to check that out, link is in the video description below, or you can check it out on trevtutor.com. So I wrote this exam. I took some questions from the free book, The Book of Proof. You can check it online. Type in The Book of Proof on Google. It'll be one of the first results. And I also took some questions out of the videos and altered them a little bit. So this covers proofs, functions, relations, and finite state automata. So hopefully you check that stuff out. If any of this material was not covered in your course, feel free to skip those questions and just tally up what you got on the stuff that you should know. So we're going to do some proofs here. Here's a nice one. If A divides B and A divides C, then prove that A divides B and C, or B plus C. So you can use direct proofs, contrapositive proofs, proof by contradictions. This one we're going to use a direct proof. And okay, so here's the thing. If A divides B, then this is the same thing as saying that A times some number K is equal to B. Because A divides B, so some number K, so B divided by K is equal to A. Okay. If A divides C, then this is saying that A times some number J is equal to C for the same reasoning. So let's take B plus C. B plus C is just equal to AK plus AJ. So we can factor out an A. So we get A times K plus J. Therefore, A times some number, K plus J, is equal to B plus C. Therefore, A divides B plus C. So that was the first proof, 3 points. 1 point for this step, 1 point for this step, and 1 point for your conclusion. Actually, this would be 2 points for that step, because it's pretty much all together. Okay, here's a question. If n is an integer, then 5n squared plus 3n plus 7 is odd. This is sort of a tough question. So we have two cases. Case 1, n is odd. So if n is odd, then what is 5n squared? Okay, well an odd times an odd is an odd. Okay, so 5 is an odd. So an odd times an odd times an odd is odd. Okay, so 5n squared is going to be odd. Okay, what about 3n? Well, 3 is odd, n is odd, so an odd times an odd is going to be an odd number. Okay, what about 7? 7 is odd. Okay, so this is an odd plus an odd plus an odd. So what is an odd plus an odd plus an odd? Well, it's odd. Okay, so case 2, we say n is even. So if n is even, then n squared is even, and what is an odd times an even? Because 5 is odd, so 5 times n squared would also be even. Okay, if n is even, then 3 times n is going to be even, because an odd times an even isn't even, but 7 is odd. So in this case, we get an even plus an even plus an odd. And what is that? Well, that's odd. Therefore, 5n squared plus 3n plus 7 is always going to be odd. So, proof, 2 points for the cases, 1 point for the conclusion. Okay, here's a trickier question. Suppose a and b are integers. If both a, b, and a plus b are even, then both a and b are even. Okay, so we have to do a contrapositive proof. So here's the thing. If we have a even and, this should be ab even and a plus b even implies that a even and b even. So the contrapositive of this is going to be a odd or b odd implies that a b odd or A plus B is odd. So, whereas there's two cases that we can look at. Case 1, we have an odd and we have an even. So we could be A odd, B even, or A even, B odd. Well, in that case, then A times B is going to be an odd times an even, is going to be an even. But A plus B is going to be an odd plus an even, and we know that's going to be odd. So we have A plus B is odd. So this implies that one of those is going to be true. So the whole thing is true. We have another case. We have case 2. Case 1, case 2. Because we have A or B odd, then we could pick the case where both of them are odd. If both of them are odd, then A times B is going to be odd, because an odd times an odd is an odd, but A plus B is going to be even. But because we only need one of those two to be odd, we know that A odd and B odd is going to make A times B odd. So in this case, because both of these conditions satisfy our conditional, we have a proof by contraposition. So that question was probably the trickiest. It's worth 4 points, so you get 1 point for the conditional statement turning it into its contrapositive. You would get 2 points for the case, and then 1 point for the conclusion. Okay. Here's a trickier question. Using proof by contradiction, show that if A and B are sets, then A intersection B minus A is equal to the empty set. So I'm specifically asking for contrapositive. So what do we have here? We have, suppose that A intersection B minus A is not equal to the empty set. So what we're saying here is that there exists some element X in our universe such that X is going to be in A intersection B minus A. Okay, so if X is in A intersection B minus A, then that means that X is going to be in A and X is going to be in B minus A. So X is in A and X is going to be in B intersection A bar, since that's the definition of the difference. So that means that X is going to be in A and X is going to be in B and X is going to be in A bar. So what's the problem here? Well, what we're saying here is that X is in A from this line, and this line over here says that X is not in A. So here we have a contradiction. So there's that, and this forms a contradiction. So by contradiction, the proof is complete. Because we assumed that there is an element, but if there is an element, we have a contradiction, therefore there cannot be any elements. So that was a proof by contradiction. Any other proof that did not involve contradiction would have been A0, because the question specifically asked for contradiction. So we have to prove the following statements about sets. You can use set laws. Because this is not set theory section, I'm allowing set laws because this is a proof section. So A union B minus C is equivalent to A union B intersection C bar, by definition of the difference. So with the distributive properties, this is the same thing as saying A and C bar union B and C bar. So this is by the distributive property. Okay, so then by difference, this is the same thing as A minus C union B minus C. So the proof is complete by set laws. What you could do is say X is an element of A or B minus C, X is an element of A or B intersection C bar, so X is an element of A or B, and X is an element of C bar. And you could do that, but that's unnecessary, and this key part here, you can use set laws if you wish. That's the key part. If I say you may use it, because it's much faster. Okay, Here's a good one. Prove the following using mathematical induction. Most people do not know the formula for I cubed. So I greater than 1 to n for I cubed. Sorry, this should be I equals 1 up to n for I cubed is really n times n plus 1 over 2 all squared. So that's the formula for it. And here we prove it. So I'm going to do some algebra here. For the base case, we have to check to make sure that n equals 1 is true. So 1 cubed is equal to 1 squared times 1 plus 1 all squared over 4. So this is the same thing as 1 times 2 squared over 4, which is just 4 over 4, and that's equal to 1. Okay, so the formula works for the first step. So now we do the induction hypothesis. And we say that n less than or equal to k is going to be true, and we want to show that n equal to k plus 1 is true. So, what do we have here? I should keep the original formula on screen so we can check what we're doing. What we want to say, we want to show that 1 cubed plus 2 cubed all the way up to k cubed plus k plus 1 all cubed is going to be equal to k plus 1 squared, because we're substituting n with k plus 1. This will be k plus 1 squared times k plus 2 squared all over 4. Okay, well, we know that n less than or equal to k is true, so 1 cubed plus 2 cubed all the way up to k cubed is the same thing as k squared times k plus 1 squared all over 4. So then we just add k plus 1 all cubed, and that should be equal to the right side. So I'm not going to write the right side every single time, because that would take too long. So now we should probably get these things under a common denominator. So that'll be k squared times k plus 1 all squared plus, okay, we need to multiply this by 4. So 4 times k plus 1 cubed all over 4. Okay, so what do we do now? Well, we can factor out a k plus 1 squared, so let's do that. That should make things a little bit easier. So we factor out a k plus 1 squared, so we get k squared plus 4 times k plus 1. This will be all over 4. Okay, so let's expand this. So this is going to be k plus 1 squared times k squared plus 4k plus 4 all over 4. Okay, so that's going to be k plus 1 squared times, well, we can factor this. So this is going to be k plus 2 times k plus 2, so that'll be k plus 2 squared all over 4, and I'm pretty sure that's what we were looking for. So we were looking for k plus 1 squared times k plus 2 squared over 4, and we got that here. So, by induction, we have proved it. So if you want to see the full thing written out step by step, just like this, it'll be on the webpage. So we've proven step by step that these two are equivalent. Okay, here's a little bit of a trickier question. I want to prove that the function f from the set of reals to the set of reals defined by f of x equal to x plus 1 cubed over x minus 1 cubed is bijective. So to do that, we have to show that the function is injective and surjective. So let's show it's injective. So what we have to prove is that f of x1 equal to f of x2 implies that x1 is equal to x2. So what we're going to do is we're going to have x1 plus 1 over x1 minus 1 all cubed is equal to x2 plus 1 over x2 minus 1 all cubed. So what I did was I just grouped the cubes together and made it the whole thing. Because now what I can easily do is say, okay, this is the same thing as x1 plus 1 over x1 minus 1 is equal to x2 over, or x2 plus 1 over x2 minus 1, because we just dropped the cubes. Okay, so now we can cross multiply. So we have x1 plus 1 times x2 minus 1 is equal to x2. The screen's being a little bit difficult there. So this is the same thing as x2 plus 1 times x1 minus 1. So we can multiply this out. This is going to be x1, x2 minus x1 plus x2 minus 1 is equal to x2, x1 minus x2 plus x1 minus 1. So that was just some expansion on both sides. Let's make this look nicer. Okay, there we go. So let's bring all of our x1s to one side, all of our x2s to the other side. This x1, x2, and this x2, x1 will cancel. When this negative x1 goes to the other side, we're going to get a 2x1 on the right. When this negative x2 comes to the left side, we're going to get 2x2 on the left. And this negative 1 and negative 1 will cancel. So we divide both sides by 2, and we get that x2 is equal to x1. So we've proven it's injective. Now, surjective is a little bit more difficult. Basically, we want to find an inverse. So we're going to let y equal to x plus 1 over x minus 1 cubed. And we want to make this a function of x. And it has to be in the set of real numbers. So we know that the cubed root of y then would be equal to x plus 1 over x minus 1. This is where it gets tricky. What we have here is we have the cubed root of y times x minus 1 is equal to x plus 1. Okay, well, let's expand this. So this is the cubed root of y times x minus the cubed root of y is equal to x plus 1. Let's group our x's together. So we're going to get the cubed root of y times x minus x is going to be equal to 1 plus the cubed root of y. Okay, now let's factor out an x. So x times the cubed root of y minus 1 is equal to 1 plus the cubed root of y. So x is equal to 1 plus the cubed root of y over the cubed root of y minus 1. So here's the question. Is this in the set of real numbers? And the answer is yes. So therefore, it is surjective. And because it is both injective and surjective, we have concluded that it is bijective, since bijective functions are just functions that are both injective and surjective. So why do we need it to be in reals? Because we're mapping f from real to real. So it should be real whether its inverse or its regular verse is taken. Regular verse is not a word, just made it up. So that's fairly difficult. But if you can do that question, you're pretty much good for any of the function questions. So here's some relation questions. We have the relation AB, AC, CC, BB, CB, BC. And we want to know if it's reflexive, symmetric, or transitive. So what I'm going to do is I'm going to draw out the relationship. So we have A here, we have B here, we have C here. Let's see which way it goes. Okay, A goes to B, A goes to C, C goes to C, B goes to B, C goes to B, and B goes to C. So we get a nice little pattern like this. I'm going to do the reflexives in orange so it's a little bit easier to see. Okay, here's the question. Is it reflexive? Well, no, it's not, because we don't have AA. So A is not pointing to itself, so clearly it can't be reflexive, because otherwise we'd have that, but we don't. Is it symmetric? Well, we have AB, but we don't have B going back to A. So no, because we don't have BA, and we don't have CA. Because we have A going to B and A going to C, but we can't get back to A. So what about transitive? Is it transitive? And the answer here may surprise you. The answer is yes, it is transitive. So for instance, if we have A to B and B to B, we have A to B. If we have A to B and B to C, we have A to C. Okay, if we have A to C and C to B, we have A to B. If we have A to C and C to C, we have A to C. If we have C to B and B to C, then we have C to C. So your question is, well, hold on a second. We don't have B to A, we don't have C to A, and we don't have A to A. Well, because we're never going back to A, we never need to worry about those situations. So we can test out all the other possibilities that we need for transitivity. So again, if you remember the definition of transitivity, if A are B and B are C, then we have A are C for all A, B, and C. So if the beginning is met, then the consequent has to be met. All the situations where the consequent do not exist, or sorry, the antecedent does not exist, it's still true. So although, what about C to C and C to A? Then we need C to A, but we don't have C to A, so we don't need to worry about it. So I expect 4 to 6 on this. The transitivity might have been tricky. Okay, which of the following operations are equivalent classes? So equivalence classes are when they are symmetric, when they are reflexive, and when they are transitive. So let's take a look at the greater than or equal to. Here's the question: is it symmetric? So is 4 greater or equal to 3 the same thing as 3 equal or greater than 4? Can we have that? No, we can't. So this one is not going to be an equivalence class because it's not symmetric. Okay, what about the equal sign? I'm going to tell you right away, this is yes, because equivalence, equals sign. Why is it called an equal sign? Because it's an equivalence relation. So if, for instance, let's say 4 is equal to 3 is equal to 4, well, it's true because 4 is not equal to 3 and 3 is not equal to 4. So the conditional for transitivity is still true. So kind of cool, but equal sign, equivalence, it's pretty straightforward. You cannot find a counterexample. So if you cannot find a counterexample for symmetry, flexivity, or transitivity, it's likely going to be an equivalence relation. Okay, here's the last one, less than. Well, same example as above. If we have 4 less than 5, is it the case that 5 is less than 4? The answer is no. So this is not an equivalence relationship or an equivalence class. In fact, it's not even reflexive. So is 5 less than or equal, sorry, is 5 less than 5? No, it's not even reflexive. Okay, enough about relations. Let's do some pigeonhole principles. Here's the question. Consider a square whose side length is 1 meter. Select any 5 points from inside the square. Prove that at least 2 of these points are within root 2 over 2 meters of each other. So, what do we do here? Well, we're selecting 5 points, and we have to prove that at least two of something. So we probably want to use the pigeonhole principle. So, here's our square. It's 1 meter by 1 meter. We need to select 5 points. So, well, what can we do? We can split this square into 4 quadrants. So each of these quadrants are going to be a half a meter by a half a meter. So if we select 5 points, then at least 2 points are going to have to be in the same quadrant. So we just have to prove that these quadrants are at least as small as root 2 over 2 meters. So the longest distance that can be in this square are root 2 over 2 meters. So let's check out the hypotenuse here. What is the distance of this hypotenuse x? Okay, well, x is going to be the square root of 1/2 squared plus 1/2 squared. That's going to be the square root of let's see, 1/2 squared is going to be 1/4 plus 1/4. So this is the square root of 2/4, which is root 2 over 2. So the hypotenuse in each quadrant here is going to be root 2 over 2 meters. So when we place our points down, let's say we pick random points. Let's pick the furthest possible combination of points. So we have one here, one here, one here, and one here. Well, it doesn't matter where I go, because even if I put one in the middle, these points are at least root 2 over 2 meters from each other, because the hypotenuse is root 2 over 2 meters. So this is the furthest we could possibly pick these points apart, and they're still within root 2 over 2 meters from each other. So by the pigeonhole principle, we have proven this statement to be true. So that was just Pythagoras and some fancy squares. If you check out my pigeonhole principle video, I did something at the end very, very similar to this, just with different numbers. Here's another pigeonhole principle question. If 15 numbers are selected at random, at least 3 of them will have the same remainder when divided by 7. Okay, what happens when you divide by 7 and you look at their remainders? So you have the set of remainders. The set of remainder can be 0, can be 1, 2, 3, 4, 5, or 6. So how many choices do we have for remainders? We have 7 choices for remainders. So if we put 15 in there, that means that we put, we can put 7 into 0, 1, 2, 3, 4, 5, 6. We could put another 7 into 0, 1, 2, 3, 4, 5, 6. And then that 15th object is going to have to go in either 0, 1, 2, 3, 4, 5, or 6. So by pigeonhole principle, we know that it is going to be the ceiling of 15 over 7, which is equal to 3. So by pigeonhole principle, you have that proof. Because there's only 7 choices, you have 15 numbers, so 7, 7, and then you still have an extra one left over. Okay, and that same question was done in the video as well, just with sums instead of remainders. Okay, here is the Euclidean algorithm. We need to find the greatest common denominator of 69, 39, and 544. This question does need a calculator, so I'm terribly sorry if you're thinking, hey, I can do this without a calculator, but you probably cheated anyway and used one, so don't feel bad. So we need to use the Euclidean algorithm. Well, we don't need to, but I didn't say you have to, but you could. So GCD of 69, 39, if we remember how the algorithm works, we take 69, 39, and it equals 544 times some number plus a remainder. So we can put 544 into it 12 times, and then we get a remainder of 411. I have the calculator done, so these numbers are correct. So that means that the GCD of 69, 39, 544 is equivalent to the GCD of 544 and 411. So in the next step, we take our old second number in the GCD, and then we do it with the remainder. And that's by the Euclidean algorithm. So in the next step, we have 544 is equal to 411 times some number plus the remainder, so 411 times 1, and then you get 133 as a remainder. So then we take a look at the GCD of 411 and 133. So I'm going to give you guys the answers, and we'll see how this pans out. So 411 is equal to 133 times 3 plus 12. So then we take the GCD of 133 and 12, and we get that 133 is equal to 12 times 11 plus 1. So then we take the GCD of 12 and 1, so we know that the GCD is just equal to 1. Because the greatest common denominator of 12 and 1 is just 1. Okay, so that was the Euclidean algorithm. It is kind of obvious that it is 1, because if we take a look at these numbers, we have that this number is divisible by 3, this number is divisible by 2, and you can kind of work your way through the rules for basic numbers and check that, hey, this is actually not going to be divisible by pretty much anything but 1. So you could do that. You could have other intuitions, but the Euclidean algorithm is the safest way to go and would get you 4 points because it has explanation. Here's a tough one, especially if your class did not cover this. That's why it's the very last question, because your class might not have covered finite state automata. So using sigma, the alphabet is AB. We want to accept any string with 2 consecutive B's. So what this means is we take, say, the strings ABBA, maybe we take the strings ABB, or BBA, or BBBBBA, or maybe even BAB. So it just needs to have at least 2 consecutive B's. So to start off our finite state automata, we need a start state. So we'll call this Q0. And what it's going to do is, I'm going to make this a little bit smaller, is when we get an A, it's just going to loop back to itself. So it's not going to accept anything with just an A, so it might as well loop back. When we get a B, because we need 2 consecutive B's, we have to track the B's. So if we get 1 B, it's going to go to the second state, and not accept yet, but if it gets another B, it's going to go to the accept state, because we now have 2 B's in a row. So as soon as we have 2 B's, it doesn't matter what we put afterwards, so we can do A or B, but there's one more case. What if we get to the first state here, we get a B, but then we get another A? Well, we want to put it back to the first state, because we need 2 consecutive B's. So if, for instance, if we just looped it back, then it would accept the string BAB, but that's not okay. So we have to loop it back to the first state so we can reset our B tracker. So that was the midterm. It's much more difficult than I think the first one was, and probably even more difficult in some aspects than the final I wrote. That's been up on the website for a bit. So if you want to know the point breakdown, it's a little bit different than the last one. Basically, anything over 90% would be an A+, and the fail would, why did I write that? 90, an A+ is, I don't know what I'm doing here, 90%. Anything over 90% would be an A+, an A would be 85 plus, and this would go down to an F, which would just be anything below 40%. And of course, if there were topics you didn't cover, just subtract it from the total and figure out what you got. So hopefully you guys did really well. If not, you can leave comments below. There's a link to this midterm in the description, and there is a subreddit at reddit.com/r/TrevTutor where you can ask other questions. If you want to contact me for anything else, my website is here, trevtutor.com. I'll try not to cross it out. And there's a lot more materials on there, so feel free to check it out, other courses as well. So hope you guys have a great day, and I wish you guys luck in your exams, because that's probably why you watch this video. So good luck in class.